Assalamualaikum warahmatullahi wabarakatuh. So Alhamdulillah, we have at least around 29 attendees. I believe that some of you will be share equipment to join our class today. So thank you very much for your response. So we start with Kitab Al-Fatihah. So Alhamdulillah, this is our second lecture for nuclear physics, SFG 4093. Okay, I need to check a few things. All right, we're gonna start now. Everyone, please fill up the attendance form. You can check from the Q&A session. All right, you can fill up right now. For those who using PC or laptop, then it can easy for you. Those who using mobile, sometimes you will lost the session. So you can try to fill up anytime. Okay, maybe you can copy the Google form. Sorry, Microsoft form. The form itself. All right. Okay, few announcement before we start. Last week announced that we should have a physical tutorial lesson for this week as a schedule. However, after check a few things, because we will not start our tutorial yet, and since that we only discussion on the introduction of the nuclear physics, so maybe we start the tutorial. We have the tutorial when we touch for the lecture number 3. Alright, when discuss about more on the binding energy and the properties of the nucleus. So I will postpone our tutorial to another week. Maybe it's not next week, but another week, maybe 13, 14 and 15. That's for tutorial for TSE1, TSE2 and TSE3. But I will announce later. So I need to upload the tutorial first. You need to do it at home, and then we can discuss in the tutorial session. All right. Hopefully after Raya, we can meet for the lecture. I'm not sure. For this moment, we need to do the online lecture, and tutorial will be the physical part because of the size of the class. So hopefully after Raya you can have some changing because of the announcement of the endemic, but it depends because lepas Raya lagi exposure lagi tinggi kan. Okay. So just a recap of what we have discussed last week. The introduction of the basic concept of the nuclear physics or the nucleus, and I believe that you have learned before, and it's a part of a recap, the terminology used in the nuclear physics, and you can see that they have a lot of information in the periodic table. Okay, this is the complex one. Okay, you can see that the number of atoms used to arrange the arrangement of the atoms itself in the periodic table, 1, 2, 3, and we call it as a number of atoms, and it consists of the numbers of proton inside the elements. And when we discuss about number of proton, it reflects the number of electrons. And then we have another things here, which is we can see that below the helium or everything. Can need to make Okay, laser pointer. Okay, example helium here 4, we have lithium 6.9, 4, beryllium 9.01. We call it as a number of mass of the atoms. Okay, so mass of the atom, the roughly calculation, we just add the number of proton and neutron. Okay, because both proton and neutron is a nucleon. The combination we create the nucleus of the atomic structure. Right. However, you can see that the number of mass is not the integer. It's not exactly 12, 14. Go for details, and they have a point something. Okay, point something means that they have a something or calculation to measure the mass of the atoms. And so that's what we try to discuss today. To see the certain example, and let's see that you can understand the what we call as the binding energy or the strong force of the nuclear. Need to silent. Right. And the number of mass of the atom, as we discussed last week, depend on the carbon. Okay. Okay, this is what we discussed last week, the nuclear mass, right? And using the unified mass unit, which is U, or sometimes using the atomic mass unit, AMU, or you can use the symbol Dalton. All of this is the same value. And the definition will be 1U, 1 atomic unit, or unified mass unit, which is equal to 1.66 times 10 to the power minus 27 kilogram. And by measuring that from the experiment, you can get the number mass of the carbon, 12.01. And by doing calculation using the E equal to mc square, finally can get the energy of the 1 atomic unit as 1 joule, and then convert to the electrovolt or mega electrovolt to become 6.242 times 10 power of 12 mega electrovolt. Sorry, this is for 1 joule. So because 1.492 joule, what we have here is for 1 atomic unit is equal to 931.5 mega electrovolt per C square. Since that, we want to get this value only, E. Alright, so, and just the C, this value here, which is including the C square. Means that when we rearrange here, we have E is 931.5 over C square. So we not calculate the C square here. So we have the number of the one of atomic unit. For the mass will be the energy will be 91.5 mega electrovolt. And from there we can measure the number, the mass of the proton, electron, and also the neutron. You can see that the proton and neutron is actually very near. The value is very near 1.00 something. However, the mass of electron is really small compared to the proton and neutron. Right? So you can get this 10 power of 1, 2, 3, 4. Okay, 5.49 10 power of minus 4. This is very small compared to the mass of proton and neutron. That's why the total mass of the atom itself is 99% from the nucleus. They have another term, relative atomic mass. That's why you can see in the periodic table, okay, the number which is the average weighted mass for the isotope. So they have another term, we call it isotope, and I believe that you will learn a bit about the isotopes. So today we can go a little bit about the isotopes, and then we can see the binding energy. And the last one will be the deuteron and deuterium. And we discuss about the example of the simple part of the element, which is deuterium. If you have any question, kindly write in the Q&A session here, Q&A slot here. So I try to answer. If you miss something or sometimes the explanation is not clear, please just announce in the Q&A. All right. Okay, let's move to the isotope. Right, and what is really isotope? Okay, and we have the example of the chlorine with the 35 number of mass or atom. So 35 itself is a mass, okay, mass of the chlorine, right? And do you remember chlorine? What is the number of atom for chlorine? Okay, we can check from the. Oh, I need to use this. Okay, chlorine here. Okay, number of atom is 17 and the mass itself is 35.45. So mass number is 35. 35 minus 17 means that what? 17 plus 17, 34, 18. 18. Okay, what is that? 18 is the number of the neutron. Okay, I need to move fast here. Okay. But chlorine also, I cannot say that it's a twin. So they have another element, dah macam berbual lah element lah kan. Okay, so they have another element with the mass number 37, which is higher than the original chlorine. So for isotope with the same chemical properties, which is chlorine, they have a same number of proton, Z. So means that you can see that the number of proton is actually 17 for the chlorine. So both chlorine have the same number of proton, but they have an additional neutron. So we have here neutron, which is 18. All right. So for the isotope of the chlorine, they have a number of neutron 20. So that's what we call as a isotope. And do you know any type of isotope in the periodic tables? Can you share with me? They have several numbers of isotopes in the. Okay, 17. Yes, 17. So do you have any isotope? Okay, type of isotopes that different other than the chlorine. Do you know any type of isotopes? You can share from at the Q&A types of the isotopes. Carbon, okay. Yes, carbon have a they have their own isotope, okay. Okay, carbon. And then we have hydrogen, also have isotopes. They have several atoms that have the isotope, and I believe in nuclear part, nuclear atom, uranium, everything, they have a lot of the isotope. Okay. So carbon, yes, carbon 12, carbon 13, carbon 14, lithium also have the isotope. Okay, hydrogen, yes, hydrogen have the isotope. Uranium, that will be the most popular. Uranium. So the uranium. So then after this, you can at the end of this lecture, I think maybe for the next another couple of weeks, then you can see that what happened to the uranium. Alright, so the chlorine isotope actually stable against the radiative decay because there are certain atoms have stability into the radiation, but the certain atom have very reactive. Okay, another part of the isotope, we have here hydrogen with the different number of neutron. Okay, so the original one. Okay, the real one of the hydrogen will be atomic number 1, which is number of proton, and also the mass number 1 because hydrogen doesn't have a neutrons. So goes for the deuterium, they have 1 neutrons, so it becomes mass number 2. For tritium, okay, tritium, we have 3 mass number, which is the neutron 2. However, in the example, we have a gas of hydrogen, the number of deuterium actually 1 in 6,000, maybe less than 1%. It's very small, or less than 5%. For tritium, yes, really small amount of the number inside the whole hydrogen cloud example. So really we can meet the tritium. Okay, the tritium we can see still have there 1 in the 6,000, but majority will be the hydrogen. So this will be important to calculate the relative mass. Okay, Lisa. So here uranium, we have U35, U38, 238. And the majority will be the U38. Okay, plutonium, nitrogen, okay, uranium, oxygen also have, bromine. Good. So we have a lot of isotopes. Element. All right. The calculation of the relative atomic mass. So how they can get the number of the mass in the periodic table. So this is example on the chlorine. So this slide, this page doesn't have. I didn't put in the slide that I upload in the goals. Okay, a few moments ago. Maybe I can upload the updated version. So this is the chlorine. Okay, has a 2 stable isotopes, 35 and 37. Chlorine 35 and chlorine 37. So this is how they mention our number of the chlorine itself. So the sample chlorine analyzed using mass spectrometer. This is experimental tools. Okay, use as mass spectrometer. It's very big. And then from there they can the following isotope abundance were calculated. Okay, so from the numbers of chlorine, they can measure the percentage of chlorine 35 and chlorine 37, as I mentioned for the hydrogen. So chlorine 35, the percentage, the abundant percentage would be 75%, means that in the certain amount of the chlorine, we have 75% chlorine 35. Only 24% is a chlorine 37. So to calculate the relative mass, atomic mass of the chlorine itself, so this is the equation itself. Isotope abundance, which is the percentage, 75.8%, which is 0.75 here. And then we have the isotope mass. The isotope mass itself is 35. And then we have isotope abundance for the chlorine 37, which is 224%, which is 0.24 times the 37, which is the isotope mass. And after the calculation, we can get the relative atomic mass, which is 35.484. And that's appear in the periodic table. Maybe you can check the periodic table here. Okay, here. Okay, 35.5. Okay, dia bundarkan situ 35.5. So maybe you can check the original periodic table. If the chlorine itself, 35.5. 0.45. Okay, they have a error calculation there at the end, but this is same very near, okay, value, can say that. So this is not for chlorine only. We can calculate for the hydrogen and the lighter atoms. So this is what we call as the relative atomic mass of the chlorine. Okay, this I found is a visualization on the chlorine isotope, all right, and how they measured the relative mass and the abundance. All right. Other than isotope, we have isoton and isobar, which is the isoton nuclear with the same number of the neutrons. Okay. Okay, same number of neutrons but different number of the protons. Compared to the isotope, they have proton which is positive charge, same thing, but they have neutron n inside, additional neutron. But for isoton, opposite, they have the same neutron but the different number of proton. Isobar, it has the same number of nucleons, means that neutron and proton same, but then it has a different number of protons, but it's a different number of the proton and neutrons, right? Okay, and we can go straightly to the deuterium. Bila buat online dia laju pula. Miss, dia masuk dalam physical class ni tak sampai lagi sini katanya. Alright. Okay, deuteron, this is the isotope for the hydrogen. And first question I want to ask, what the difference between deuteron and deuterium? Okay, this deuterium, they have another thing we call it as a deuterium. Okay, deuterium. So if you know what is a, if you can, okay, they have here. I need to change the pen here. Okay, this deuterium, deuteron. Can any of you explain the difference between both of these? Deuteron and deuterium. It's a terminology, but I think it's way clear a little bit about the term used in the deuteron or deuterium. Right? Alright, do you know the difference between deuteron and deuterium? Okay, so the combination or the bond between one proton and neutron, we call it a deuterium, deuteron, okay, which is the simplest compound nucleus. So deuteron is something like the nucleon. Okay. So because of the hydrogen doesn't have a neutron, the original one, okay. Deuteron is the nucleus of the deuterium. Deuterium is isotope of the hydrogen. Okay, good. Good answer. Deuterium is the nucleus of deuterium. Okay, jadi macam nukleon pula kan. Okay, nucleus lah. Alright. So the combine of the neutron proton will form a deuteron. Okay. Okay. So the atomic structure or the atomic or the chemical element that they produce from that we call as a deuterium. Okay. So the deuterium nuclear mass actually 2.013533 atomic units. unit, which is came from the experiment. The deuterium atomic mass actually 2.014. So it's not we can see that it's quite similar nuclear mass and the atomic mass. However, they have a certain difference here, 0.001. Okay. Oh, sorry. Oh, less than that, which is 0.005. 0.0005. Okay, half of that. Okay. Sorry, this part of the different, one of them will be the mass of electron. Yeah. They have one electron. So they have another balance, number of the mass of the atomic unit there. So and that follow the electron binding, okay, 13.6 electron for deuterium. We can neglect, okay, because nuclear binding is about 1 million times greater, okay, which is bigger than that. So the electron binding we neglect. So fortunately, because this is only have one electron, so it doesn't affect too much. If we have more than one electron, that's why it's very difficult to calculate manually when we try to solve the Schrodinger equation itself. So imagine here, if we have one proton and one neutron, okay, this is a part of the idea of the deuterium. But if we measure separately, one proton, one neutron, we know the mass of the one proton, which is 1.0 something. We have one neutron, we know the mass of the one neutron. We add both of the proton and neutron, so we can get the value actually 2.015941 atomic unit. However, the deuterium nucleus result from the experiment, they measured, they get 2.013553 atomic unit, which is smaller from the theoretical. Because we combine the mass of the proton and the neutron, okay, this is the value. So they have difference between the combined and without the combined. We imagine we have A and B, okay. A have certain mass, okay, 50 kilogram. B, they have another mass, maybe 60 kilogram. If we stay together and we hold hand and measure the mass, it should be 60 plus 50, 110. However, it not happen like that, okay, because they have what we call as a binding energy. Okay, the mass of nucleus is not equal to the sum of the mass of the each part. Maksudnya kalau kita measure satu-satu, sepertinya kita dapat amount tadi lah, seorang 50 kg, seorang lagi 60 kg, combine, we can get 110 kg. Tapi dalam deuterium nucleus, when they combine, the exact mass tu dia tak jadi spesifik 110 kg yang macam kita bincang tadi. Mungkin sebabkan dia pegang tangan kuat sangat tu, dia jadi mass dia jadi kurang daripada 110, mungkin 105. Okay, less 5 kg loss. So 5 kg loss tu ke mana dia menghilang? Okay, that will be the idea inside the deuterium. If we see physically, maybe it's not logic, but because it happened very, very small. That's why the physical part, when we measure our mass, doesn't affect anything because of very small effect on that. But for atoms, it happened and it create a lot of different on that. So we know the mass of the deuterium, okay, the combination of the mass of the neutron and proton, and then we have another mass we call as a binding energy here. Okay, so this, so here should be 2.01541. MD should be 2.013553. If we measured it, we can get the amount of the delta M, which is the we call as a binding energy. Okay, the lost mass is converted to the nucleon binding energy, which is equal to delta E equal to B, so equal to delta M C square. So that's why we put delta M here is equal to B over C square. So that would be the binding energy of the nucleons. So from the calculation, they have some way to do the calculation. First, we add an electron here on the left and on the right. So we have here electron from the same equation. So we know that MD plus ME here. So MD plus ME here. Okay. So it's the deuterium mass, the atomic deuterium mass. Okay. And for the MP plus ME here, MP plus ME here is the hydrogen, because hydrogen doesn't have a neutron. So this one is hydrogen. So this one for the deuterium. All right. So we can add here mass of the deuterium here and mass of the hydrogen here plus the neutron. We can get the binding energy. Okay, so convert this. This I have mentioned why we neglect the binding energy of the electron. So now we can put the value. Okay, we rearrange B over C square binding energy, move to the left. All right, and then hydrogen, the deuterium we put here, deuterium. So we put the value here, mass of the neutron, mass of the hydrogen and deuteron. So total up this, this one mass of the hydrogen plus the neutron minus the mass of the deuterium. Finally, you can get the value of the difference between both will be 0.002388 atomic unit. So this what we call as the binding energy over C square. So convert U, the atomic unit, to the 931 times to the 931 mega electron volt per C square. And finally, we can get the value is 2.2 mega electron volt per C square. So that's what we call as a binding energy of deuterium. Alright. So everyone clear the calculation? It's very simple here. Okay, just Eklan, those who please fill up the attendance form. Okay. Takut terlupa nanti. So worried that we will forget about that. So please fill up the attendance form. You can check link at the chat. Okay, we have 47 respondents. So thank you very much for that. Okay, when we discuss about the binding energy, we have here potential well. Okay, we have potential well of the deuterium. And the graph itself is energy versus the distance. Okay, this is the distance. Distance what? Okay, here is R. Here is R. Okay. So R is the radius of the nucleus. Why? Because we know that the nucleus itself they have a shape with a sphere. Okay, so R is a radius. R, capital R. The small letter of R is a binding energy or the distance between proton and neutron. Okay, so we have proton and also the neutron. So this will be the distance. Okay, the distance will be R. Okay, small r. Inside the nucleus, which is the R capital. Macam Mr. Potato pula. Okay, so so the radius for the sphere here is a capital R. And the idea will be R small, okay, the smallest R should be less than the radius of the nucleus itself. Okay, because if the distance between neutron and proton more than the radius of the nucleus, so the binding will split. Okay, maksudnya terputuslah akad nikahnya. Lebih kurang macam itulah. So tak boleh lebih daripada radius of the sphere. Okay, that will be the rules. So when they have less than radius of the sphere of the nucleus, then it create what we call as a binding energy of deuteron here, binding energy. Okay, so this is the minimum energy which is the potential well. Okay? And so here the definition R small, separation or distance between the proton and neutron. And then we have the potential itself. Okay? So for R less than capital R, you can get a value of the potential energy will be negative 35, certain book negative 20 megavolt. But above that, there will be 0. So this will start what we call as a coulomb. Okay, coulomb potential. But this one is very clear, very close. Then they have the binding energy 2 megavolt. Okay, very small. And actually, they cannot reach R equal to 0. They have a small point here, but it's really, really small here. Means that the minimum distance, the maximum distance that they can get close. Okay. And this for the R itself is 2.1, if I'm not mistaken. 1.3 femtometer, which is the size. Okay, the size of the R. Right. So this is some summary on the binding energy of the deuteron. Okay, so binding energy is 2.2 megaelectronvolt. So if the neutron and the deuteron were to decay to form a proton, electron, and antineutrino, the combined mass energy of the particle will be 2 times the 98.27 megaelectronvolt plus 0.511 megaelectronvolt. It become a 1800. Okay, but the mass of the deuteron itself is 1875. Okay, so we discussed previously the average binding energy per nucleon is 7 megaelectronvolt for typical nuclei. Okay, but for the deuteron is 2.24 megaelectronvolt. Sorry, 7 to 8 megaelectronvolt. Okay, it's very small. So they have some discussion on that and discussion more on the quantum. Okay, quantum part of the potential well. So they discuss about that to calculate the binding energy of the deuteron and how the graph we can get the potential well. Right. So that's all for today. Entah dia buat online class ke laju jadi kan. Right. So do you have any question? So next should be another nuclear properties. Okay. After that, then we can week number 4. It should be discussed about the model or type of model of the nuclear. Okay, liquid model or everything. Then we'll discuss about the radiation. So do you have any question? Okay, if not, then I can conclude our lecture for today for week 2. From the book of the kin, actually is a chapter. This one is chapter 4. Okay, some part of the chapter 4 and also chapter 3. So next week should be discussion on chapter 3. Okay, chapter 2 actually more on the quantum, introduction of the quantum. So chapter 3 we discuss about the nuclear properties. Okay, this one I pick the example of the deuteron and deuterium. Okay, so thank you. If you have any question, no question. Okay, thank you very much. Okay, tak faham pas part deuterium tadi. Okay. So ada yang kata tak faham tadi part deuteron. Okay, tang mana yang tak faham tu? Okay. Untuk deuteron ni, easy to say because what we can tell here, because from the experiment, deuterium when they measured, berat dia tu lebih kecil berbanding theoretical. Theoretical maksudnya dia calculate lah berat proton berapa, berat neutron berapa, tambahkan dua-dua, sepatutnya samalah dengan berat deuterium. Sebab deuterium adalah neutron plus dengan satu proton kan. However, they have a difference between the amount itself. So different tu lah yang dikaji, dan different tu pula makin kecil bukan makin besar. Okay. So that's why they predict that the balance itself create what we call as a binding energy. Digunakan sebagai tenaga yang mengikat antara kedua-dua proton and neutron itself. Okay. So itu yang menjadikan tenaga tu makin kecil apabila menjadi deuterium compare to proton and neutron itself. Oh, conclude ketara. Okay. Oh, yang tanya slide second last tadi Okay. Okay, saya pergi slide second last dulu. Second last tadi yang mana? Ni last. Oh, okay, yang potential alright. Okay, yang potential ni memang dia agak sebab dia more on ke the quantum sebenarnya, okay. So the quantum. But what we can say that sebab dia kalau ikut dalam teks pun dia akan cerita, dia akan derive the Schrodinger equation itself. Okay, saya tak pergi ke situ lah. And they have another graph actually, wave function graph to explain deuterium wave function, yang mana saya pun tak cerita details on that lah. Okay. However, you can see that they have a very small, okay, daripada graph tadi, very small amount of the binding energy here at the two, and then kalau potential well, dia kata kalau dalam satu potential ni and then less than, saya tak buka slide kat sini pula. Okay. Okay, ayat mudah dia. Potential well dalam value A to, sorry, 0 to A here, 0 to A, they have possibility that electron here. Okay, dia itu idea of the potential well lah. Okay. So means this is possibility lah. After than that, dia takkan ada elektron lagi. Gitu. So dalam situ juga dia akan dapat measure sini binding energy in this range. Okay, this range they have a very small amount of the binding energy compared to the whole potential energy there. Okay. So potential energy ni termasuk dengan elektron sekali lah. So now everything happen because proton and neutron itself, distance between proton and neutron itself, okay, very small. Okay, they have the, pada value R lah. Tapi kalau sebab dalam satu, tak tahu dah jadi ke tidak lukisannya. Okay, sphere. Okay, they have a sphere here. Alright. So they have a radius. Okay, this is the radius of the sphere. If the distance between proton and neutron is more than the radius itself, so what happen actually, binding tu putus. Okay, sebab binding itu dia punya force dia kecil je, very small there. Okay, tapi the whole force actually is very strong. Tapi dia punya binding dia tu is a very weak force here. So what happen kalau duduk dekat less than radius of the nucleus itself, then it will create the binding energy. But after that, so the value of the potential will be 0. So that's why yang neutron and proton tu akan split lah. So that's why deuteron atau deuterium, okay, deuterium tu sendiri tak sama. Tak banyak. Okay, because it's very easy to split between the proton and neutron. Because the binding energy very small. Okay, so that's why dalam hydrogen punya ni is more hydrogen compared to the very big amount of the hydrogen compared to tritium and also deuterium. Alright. So itu dia punya explanation lah. So they combine the graph of the potential well, and actually they're using the quantum inside there. Okay, so this is R is actually to find the radius. Actually, this is the radius of the sphere of the nucleus itself. Okay, so ini memang mistake 1.35. Okay, which is the radius here lah, 1.35 here. So the binding, the distance between proton and neutron should be less than this amount, so very small. Okay, so tu yang tadi lah. Okay, kalau tak clear boleh maklum balik, right? And conclude the difference between deuterium and deuteron. Okay, so deuterium is the atom itself. Okay, deuterium is the atom itself. Just like that. Okay, so deuterium is actually is the atom itself. Okay, the atom for hydrogen isotope that have proton, neutron and electron. We call it deuterium. Okay, kita namakan dia sebagai deuterium. However, the nucleus part of the deuterium we call it as a deuteron. Ayat mudah dia, deuteron dia tak ada elektron lah, dia tak ambil kira. So sebab dia kita nak calculate dia neutron dengan proton tadi. Okay, neutron dengan proton. Dia macam apa, nukleon lah kan, lebih kurang. So deuteron is like a nucleus of the deuterium. Right? So the whole atom we call as a deuterium. This one we call as a deuterium. Deuteron yang ni. Itu the simplified version to explain what the difference between both. Okay, so any other question atau tak menjawab ke? Sorry, minum sikit. Okay, thank you. Okay, faham. Alhamdulillah. For potential well, actually they have some calculation there. Okay. Related to the sign everything lah. And semua buku, saya tengok buku kebanyakan akan ceritakan itulah. So saya tak cerita details on that, on the calculation. And just look at the idea itself, what is that. Right? And the calculation the binding energy pun dia ada beberapa method sebenarnya, ada 3 method. Saya tunjuk satu method je to calculate that. Okay. Okay, I make a mistake here. So announcement patut saya rasa macam pelik sikit tadi. R besar, R capital. Okay. R capital is not a radius sebenarnya. Atau dia confusing. Sebenarnya R ni adalah diameter. R is a diameter. I'm not sure ada yang lain. Okay, diameter. Diameter maksudnya bawah logik. So maksudnya proton boleh duduk kat sini, neutron boleh duduk sini. Still in the range, okay, less than R. Faham okay, R tu diameter, sepatut radius separuh daripada sphere kan tadi. Patut saya, dia ada confused sebab bila kita gunakan R, biasakan radius kan. Alright, so actually R capital is a diameter of the deuteron. Diameter maksudnya the whole sphere tu lah, panjang okay. Radius kan separuh tu je. Right. So that's my mistake. It should be diameter of the deuterium. So the proton and neutron should stay within the compound of the sphere itself. So kalau dia terkeluar sikit je, maka terpisah lah dia. That's why this neutron can easily, because the bonding energy actually kecil sangat. Mungkin dia punya mas kahwin dia kecil kat sini lah. Okay. 2 megawatt. Just to get you to understand that. Alright, so I need to clear again. I made my mistake. R capital is not a radius, it's a diameter. Okay, the diameter means the whole sphere. Right? So the proton and neutron should be move around the sphere. Okay, kalau dia duduk hujung dengan hujung pun the amount should be R small equal to R capital. Okay, so dia tak akan terlebih. Kalau once dia terkeluar daripada the R small is bigger than the diameter of the nucleon, okay, deuteron, what happen actually, maksudnya salah satu nucleon tu dah terkeluar lah, sama ada proton ataupun neutron tu dah terkeluar daripada sphere tu saja. Right? So that's my mistake in the explanation. Okay. So alhamdulillah masih tengok dia jumpa dah. Alright. Any question before I conclude the lecture today? Okay, the last one, don't forget to fill up the form. Ada berapa orang lagi? Very small amount lah, seorang ke dua orang lagi. They not fill up the attendance forms. Okay. Mungkin ada yang masuk sekejap ke, ada hal tak ada masalah. Okay. I'm trying to upload all the video in the YouTube and then share with you the goals. Okay, depends. Sebab nak kena edit dan biasa sikit. So announcement before I conclude, this week tak ada tutorial. Okay, there will be no physical tutorial. I will announce later the tutorial. Okay, how about next week? So next week punya lecture will be unsynchronized. So I will upload a video to goals. Okay, so you can view the videos and learn about that, and they have some question on there. Alright, so that will be for next week. So kalau tak ada, wish you Ramadan Karim. Selamat menyambut bulan Ramadan. InsyaAllah kalau nampak nak bulan hari Jumaat ni ke, hari Sabtu lah puasa kan. Cuaca pun cerah. However, from the calculation should be on Sunday. Alright. And Ramadan Karim, take care everyone for the coming here. And then bulan puasa ni pun mungkin ada bazar ke, wallahu alam lah. And then hopefully we can meriahkan ITM, okay, Masjid Usim, for tarawih, everything, or maybe ada yang pergi ke nilai and surau atau surau terdekat, insyaAllah. Ramadan Karim, mana yang belum ganti puasa, ganti cepat. Okay, so see you for another 2 weeks. Okay, next week saya akan hantar video je lah untuk yang synchronous lecture. Okay, selamat puasa. Okay, terima kasih. Belum puasa tekak dah kering dah. Tak tahu lecture dia macam belum puasa ni, Allah. Yang you all pun jangan ngantuk sangat lah masa belum puasa ni kan. Okay, so hopefully unsynchronous maksudnya you can take time lah. Biasalah, biasa belum puasa schedule semua lagi kan. Biasa bangun time subuh je. Ini sebelum subuh kena awal lagi. Okay, alhamdulillah, Ramadan Karim. So alhamdulillah kita dah start endemic, so maksudnya kedai makan pun semua buka lah. Okay, thank you all. Mungkin ada yang masak tapi ada yang makan kat kedai kan. So at least adalah kedai buka, insyaAllah. Alhamdulillah. Okay, alhamdulillah. So saya pun adalah nak murih malam-malam ke tidak. Kita pergi cari teh tarik lah tengah malam kan. Okay. So alhamdulillah dah mengomel lalas saja. Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Okay, thank you everyone. Ya, selamat bertarawih. Okay. Alhamdulillah. Saya punya trik lah untuk sejak area rumah saya ni, time bulan puasa ni, minggu pertama tarawih memang confirm masjid tu penuh sampai keluar kat rumah saya lah. Jadi minggu awal ni memang jarang saya pergi tarawih kat masjid, buat kat rumah ramai anak lah. Dah lepas minggu kedua tu baru pergi, sebab biasa lengang time tu. Okay, thank you semua, thank you. Assalamualaikum. Okay, semua sama puasa. Welcome.